Hi there. In this video, we are going to be looking at the differences between strong electrolytes, weak electrolytes, and non-electrolytes. Electrolytes are substances that when they dissolve in water, produce ions. They don't produce electricity. It's a common misconception with electrolyte substances. But what they do is they produce ions, and it's those ions that help electricity flow through the solution. To help see that today, what we're going to use is this light bulb tester for electricity, or for electrolytes. And it's a simple light bulb here with two electrodes sitting down below. And currently this light bulb is plugged in, obviously though not lit right now. What's going to light the light bulb here is a connection between these two electrodes. Right now there isn't one, and electrons can't jump between two electrodes like this when they're that far apart. So to help this, we're going to allow the electrons to move from one to the other by having an electrolyte mixed in with this. Don't try any of this at home, all right? This is playing with water and electricity, or doing a demonstration with water and electricity is somewhat dangerous, and so do not try this on your own at home. You need specialized equipment for this. So what I have though is a beaker with just some plain water in that, and water, as you can see, doesn't really allow any electricity to flow through the solution in this case. And so water is a relatively poor conductor of electricity. There aren't enough charged particles in the water to allow the electrons, for the flowing electricity here, to make it from one electrode to the other. What I'm going to do though is add an electrolyte to that water solution. And I'm just going to use regular sodium chloride, NaCl. This is an ionic compound, and I'm going to start with just a small amount of that. So just a little bit on the tip of the spatula here. I will sprinkle that in to this solution. And I'm going to stir this up just a little bit, just to make sure it's all mixed in well. And now that light bulb lights up. Right? And what's going on here is the sodium chloride has dissolved in the water. As it dissolves in the water, it's breaking apart into ions, and it's those ions that help the electricity flow through that solution. And you can see as I raise it in and out of the electrodes out of the water, there the light bulb lights up, and then it goes out again because, again, I'm losing that connection. But as long as that water solution with the ions in it is between the two electrodes, electricity can flow from one electrode to the other. Remember, the solution itself is not generating the electricity here. That's coming from the power supply. What is generating, or what is allowing the light bulb to light up, is the electrons being able to flow from one electrode to the other. And so let me see what happens here. If I add a little bit more sodium chloride, I'll just add the same amount to the same beaker. We'll just sprinkle some in there, and I'll give it a quick stir and see if anything changes as a result of this. And hopefully now you can see that light bulb is even brighter than it was before. It was a little bit dimly lit before. Now with more ions in there, I'm getting an even brighter light with that. And what that's showing is that the amount of electricity that can flow through the solution is dependent upon the number of ions that you have in there, the concentration of those. The more ions that I have floating around in there, the more electricity can pass between the two electrodes. So what's happening here, let me just draw it up on the board for this. We're starting with solid sodium chloride. And what's happening is when I first put that in there, that solid sodium chloride dissolves. When something dissolves in water, we say that it's aqueous. So I put a little AQ behind that to indicate that that's dissolved sodium chloride. But as soon as it forms that aqueous sodium chloride, it breaks apart. It breaks apart into separate ions. We get aqueous sodium ions and aqueous chloride ions. And it's those ions that are helping that electricity flow through that solution and allowing the light bulb to light up. So sodium chloride is an example of a strong electrolyte. What that means, that terminology means that every single NaCl unit that I threw in there got broken apart into ions. So for every one NaCl unit, I'm getting essentially two ions, a sodium ion and a chloride ion from that. And that's what's allowing that light bulb to light up when I put that solution between the two electrodes, and it allows that electricity to flow between the two electrodes. Let me rinse the electrodes off real quickly here. So I'll just use some deionized water to rinse those off. And I'm going to dump this out in my sink here. And I've got a separate beaker with, again, just plain water in that. And so you can see there, nothing's happening with that, because again, there's not enough ions in that water to light up that light bulb and to help the electricity flow through there. This time around, we're going to try something called sucrose. This is actually just plain old table sugar. It has a formula of C12H22O11. Let's take a look at what happens when I put some sucrose into the water solution. So again, here's the same water solution. Does not light the light bulb there. And so we'll get some sucrose out of here, and I'll get a big scoop of it here because I like lots of sugar in my water. And so let me dissolve that. I'll sprinkle that around in there. And we'll stir this in again because it has to dissolve in order for it to break apart into ions. And so a good amount of that is dissolved in there. You can still see some of it swirling around at the bottom. But unlike with the sodium chloride example, the sucrose, the sugar, is not lighting the light bulb. The sugar is dissolving. Now there is some still sitting in the bottom there. The sugar, a lot of it has dissolved at this point, but there's no ions in solution. That's what that's telling us. When the light bulb does not light up, there are no ions in that solution. And so what's happening here, here's my formula for sucrose. It's C12H22O11. It's actually a fairly big molecule. That's what we started with, was the solid. It is dissolving. So it is forming aqueous sugar molecules. That's when you drink a sugary tasting drink, that's what you're tasting, is that dissolved sugar in there. But the sugar molecule does not separate. There are no ions there. And so if it's not separating into ions, that's why it's not lighting the light bulb, because there's no ions in there to help that electrical charge flow through the solution. So we say this is a non-electrolyte, whereas sodium chloride is a strong electrolyte. So that's the difference between those. So one more example that I want to take a look at here, and just as before, let me rinse this off just so there's no contamination there, no sugar or salt or anything else remaining on those electrodes. And I'll dump that beaker out. And I've got one more beaker. This one's empty though. Again, I just had some water in it, but I just poured that water out. So this one's empty. Again, there's nothing, even air doesn't help that electrical charge flow through there either. We're going to try one more substance. And this one is acetic acid. This one's a little bit more toxic. That's why I put the goggles on there, just to be on the safe side. Acetic acid has the formula HC2H3O2. It's actually the same stuff that's in household vinegar. And this is even more concentrated than the salt example that I showed you earlier. So again, here's the beaker here. I'm just going to put a little bit of that in the bottom of the beaker, just enough to cover it here. See if I've got enough in here, and take a look at what happens here. Can you see that? Right there, the light bulb is lighting up. Take it out for a second, I'll put it right back in. All right, so the light bulb is lighting up there, just not very much. Now, like I said, this is a higher concentration. There's more stuff dissolved in that water than there was in the sodium chloride example. The first one, it really brightly lit the light bulb. And yet this one is just barely lighting that light bulb. I have to hold it in there for a few seconds. Remember what we said though, is that how much electricity flows through there is dependent upon the number of ions that you have in that solution. And in the case of acetic acid, there are ions, so it is an electrolyte, but we call it a weak electrolyte. And so let me erase my sugar one here because that one wasn't very exciting. In the case of acetic acid, it's it starts out actually as a liquid in its pure form. Acetic acid is a liquid, but you can add some water, which we already had that in water there, and so it makes it aqueous, HC2H3O2, and I'll put the little AQ behind it in this case. It does separate into ions. The ions that we get here, we get a hydrogen ion from this. I'll move this so you can see a little bit better. An aqueous hydrogen ion, and we get the acetate ion, which is the C2H3O2 minus ion. But we only got some of those. It stays mostly in this form here, in its molecular form. As opposed to its ionized form. And so a weak electrolyte is a mixture of these two, where it stays mostly in its molecular form. Let's say out of 100 molecules of acetic acid that dissolved, maybe only 1 or 2 of those 100 molecules dissociate or separate into ions. That's why it does like the light bulb, but just barely, because there's a relatively small number of ions. Whereas if I dissolved 100 sodium chloride units in water, every single one of those breaks apart into ions. So you get 100 sodium ions, you get 100 chloride ions when 100 NaCl molecules or units dissolve in water. Whereas acetic acid, when it dissolves, maybe only 1 out of 100, 1 out of 1,000. It's a really, really small number of particles that actually breaks apart to give you ions. That's why it just barely lit the light bulb then in that particular case. And so in those instances, when we just get a little bit of dissociation, we call that a weak electrolyte, where there is partial dissociation. The strong electrolyte gives us complete dissociation. All right, so that's just a neat little way to illustrate this idea of strong, weak, and non-electrolytes. Strong electrolytes help that electrical charge flow through the solution really, really well. That's why it lights up that light bulb very brightly, because there's a high concentration of those ions in solution. A weak electrolyte, only a few of the particles separate into ions, and then the non-electrolyte, like the sugar example there we had, none of the molecules separate into ions. All 3 examples dissolved in water, but it's whether they produce ions when they dissolve in water. And it helps that electricity to flow through it. Once again, the electricity is coming from the outlet, all right, not from the solution. The solution's just helping that electrical charge flow through there. So remember, don't try this at home. I hope you enjoyed it, and thank you.